Okay, so welcome to this next video in which we are discussing the electron transport chain. Okay, so we have now discussed the production of reduced NAD, and we have discussed the chemiosmotic theory, which is the principle on which we are working. And what we now want to discuss is the actual nitty-gritty of the electron transport chain. So basically, this involves 5 enormous great protein complexes which are in the inner mitochondrial membrane. Okay, and we're going to begin with complex 1. Okay, so here is the inner mitochondrial membrane here. Okay, and sitting in the inner mitochondrial membrane is complex 1. Now, complex 1 is sort of L-shaped like so, and it has this one arm coming into the matrix of the mitochondria. So this is the inner mitochondrial membrane. This side again is the intermembrane space here. Okay, so this is the space, remember, that we are putting protons into. Okay, and this side is then the matrix of the mitochondria. Now, to illustrate to you how enormous this thing is, it is made up of 42 separate polypeptides. So it's really beyond, it's beyond being able to actually draw out each polypeptide, basically. So this is made up of 42 polypeptides. So it's an absolutely enormous complex of loads of proteins all stuck together to make one fantastic, enormous complex. Okay? So this is what complex 1 is. It's enormous. Now it's also got a few other names. So it's also called reduced NAD, so NADH dehydrogenase, and that reflects the fact that it is going to take that hydride anion that we gave to the to the oxidized nicotinamide adenine dinucleotide. It's going to take that off the NAD molecule. Okay, so this is, whoops, what am I doing? Dehydrogenase. So NADH dehydrogenase. Now it's also got one final name. It's also called NADH and then / ubiquinone oxidoreductase. Okay, and this reflects the fact that it's going to oxidize one molecule, and that molecule will be the reduced NAD molecule. Okay, and it's going to reduce another molecule, which will be the ubiquinone molecule. Okay, so basically that's what complex 1 is going to do. It's going to take the electrons off the reduced NAD molecule, and it's going to give them to the ubiquinone molecule. Okay, so we now need to discuss the structure of ubiquinone. So this is one of the stars, basically. Okay, so ubiquinone contains a chemical group known as 1,4-benzoquinone. So I'm just going to start by discussing the structure of 1,4-benzoquinone. Okay, so basically this is based on the structure of benzene ring. Okay, but we have attached 2 oxygens off the benzene ring. So what we're going to have is a 6-membered carbon ring, like so. Okay, we'll have double bonds between this carbon here and this carbon here, and a double bond between this carbon here and this carbon here. We'll then have hydrogen atoms off this carbon, this carbon, this carbon, and this carbon, which we won't show because we're drawing a skeletal structure. And then off these 2 end carbons here, we'll then have carbonyl groups, like so. So this is 1,4-benzoquinone. Okay, right. Now, this structure is within ubiquinone, so I will now show you the structure of a ubiquinone molecule. Now I'm going to rotate this around to put it in ubiquinone, so we'll have it like so. Okay, and we'll have our double bond here, we'll have another double bond here, we'll then have carbonyl groups off these 2 end carbons, and the reason this is called 1,4-benzoquinone is because if we call this carbon 1 here, then we can count round 2, 3, 4. So the 2 carbonyl groups are off the 1st and the 4th carbon, basically. So that's why it's 1,4-benzoquinone. Of course, if you moved the carbonyl group to here or to here, maybe it would be a different type of benzoquinone. Okay, so we have this 1,4-benzoquinone here, and I'll just finish up that little gap. And then what we're going to have is we're going to have two methyl groups attached via ester links off these two carbons over here. So you have an oxygen with a methyl group coming off it here as well. So you've got two of these where you've got oxygen and then methyl groups coming off. And then you'll have a methyl group coming off up here. And now you're going to have basically a polymer structure down here, which is going to be an isoprenoid polymer structure. So let me just explain this, because if you haven't heard of what an isoprenoid polymer is before, it can be quite daunting. Okay, so let me explain to you the structure of isoprene. So basically, isoprenoid polymers are polymers of isoprene. So we'll start off with what isoprene is. So I think firstly, it's helpful to see the molecular formula for isoprene before you actually see the skeletal formula, because the skeletal formula actually isn't that helpful because it's too simple, basically. So I'm going to show you the molecular formula. So basically, it's a 5-carbon molecule. Okay, so here are the first 4 carbons, but you'll also have a 5th carbon coming off one of these. Okay, so you've got these 2 double bonds, which are very important. And you'll have 2 hydrogens off here, you'll have 1 hydrogen off there, you'll have 3 hydrogens off here. I'm not going to be able to fit that final one in, never mind, there we go. Okay, we've got 4 bonds now off that, so we don't need to worry anymore about that. And then we have these 2 hydrogens coming off here. So this is the structure of an isoprene molecule. Now let me draw the skeletal structure for it, and you'll see why I have drawn the molecular formula first, because the skeletal formula is so simple. Okay, so here are the 4 carbons that form the sort of backbone. So this one is here, this one is here, this one is here, this one is here. We'll then have a double bond there, a double bond there, and then a methyl group coming off there. Okay, so it looks really simple there, and it doesn't, to me, that I don't look at that and instantly know what I'm talking about, whereas I look at that and instantly know what I'm talking about. Okay, so what you can do with isoprene molecules is you can polymerize them together, and the reason is that you have these 2 double bonds on the end here. So basically you can imagine breaking the second of the 2 bonds between this carbon and this carbon, and doing the same for the double bond between this carbon and this carbon. Break the second of the 2 bonds. And as always, you can imagine sending 1 electron to this carbon and 1 to this carbon. So remember, covalent bonds have 2 electrons within them, 1 from each of the 2 members of the bond. Okay, so this this bond here that we're breaking, one of the bonds in the double bond, will have 2 electrons in it, 1 from this carbon and 1 from this carbon. Imagine sending the electron from this carbon back to this carbon, and the electron from this carbon back to this carbon. Similarly, for this bond here, imagine sending 1 electron to this carbon and 1 to this carbon. This carbon and this carbon then have 3 electrons. You can forge a second bond between this carbon and this carbon by binding those 2 electrons together to turn that into a double bond. Okay, and all that will then leave is this carbon over here will have a 3 electron, and this carbon over here will have a 3 electron. Now let me kind of draw the skeletal structure for this imaginary intermediate that we are thinking about. Okay, so we've now got a double bond between this carbon and this carbon, because remember, on the skeletal structure, we've broken this bond, formed a new bond between these 2 middle carbons. Okay, and now both of the end carbons have 3 electrons, so I'll just put dots there to illustrate that. And what you can do is you can take multiple of these molecules then. So let me put another one here, like so. And you can bind this carbon here, which will have a 3 electron, to this carbon here, which will have a 3 electron, like so. And you can obviously continue this process on to form massive, great chains of things. Okay, and when you do that, when you form polymers in this way from isoprene molecules, these are known as isoprenoid polymers. Okay, so basically we're going to have an isoprenoid polymer on our ubiquinone molecule, and it's going to come off this carbon here. So here's the first carbon, so maybe this is this one here, okay? Then here's the second carbon. Now, of course, I'm not going to draw out the entire polymer. You're actually going to have 10 isoprene molecules polymerized together in this isoprene polymer off ubiquinone. I'm not going to draw the entire thing. Instead, I'm going to draw one isoprene subunit or monomeric unit, okay? And then I'm just going to bracket it and put 10 as a subscript to show, repeat this 10 times. So here's the first carbon, second carbon, third carbon, and of course you have a double bond between the second and third carbon, and then the fourth carbon up here, and then a methyl group coming off there. And then basically I'm going to take this here and we will repeat it 10 times. So I've bracketed the entire isoprene group here, like so effectively. That's what I've done. Okay, and I'm saying repeat this 10 times, and then off the final one you will put a hydrogen, and there's really no way of getting around other than breaking with the skeletal structure and saying that this is to a hydrogen. Otherwise, if you just left it, it would look as though it was to a methyl group. So you're just saying the final one, maybe this one over here, has a hydrogen coming off it, basically. Okay, so that is the structure of ubiquinone molecules. Okay, so basically, what is complex 1 going to do? Basically, it's going to take in a molecule of reduced NAD. So here comes the molecule of reduced NAD, and it's also going to take in a proton. Okay, so this is why it becomes convenient to think of NAD, reduced NAD, as working with that proton. So remember, each of the reactions which produce reduced NAD actually produce 2 hydrogen atoms. Now the NAD molecule accepts the hydride anion, and then the proton goes into the cytoplasm. But when we actually look at what complex 1 interacts with, it interacts not only with the reduced NAD molecule, but actually with the proton as well. Now obviously it might not be the same proton as actually was produced when that NAD molecule was reduced, but the principle is there regardless. Which is why some people often will denote this as NADH, and then they'll put a dot H plus, because the functional unit effectively that's going to be used by the electron transport chain is not just a reduced NAD molecule, it's the reduced NAD molecule with the proton. So basically complex 1 is going to accept 2 hydrogen atoms from the NAD molecule. Okay, so in comes the NAD molecule, which has the hydride anion with the proton, basically. They're going to come in, okay? And I'm just going to highlight that. So basically, this isn't supposed to suggest that the NAD molecule actually does go around with the proton. It's meant to suggest that they act as a functional unit. So it's a functional connection rather than a literal connection. Okay, so the reduced NAD molecule with the proton comes to complex 1. Okay, and what complex 1 is going to do is it's going to take the proton, it's going to take the hydride anion off the NAD, and it will chuck back out normal old NAD, nicotinamide adenine dinucleotide, so you'll have the positive charge again. And now complex 1 has 2 protons and 2 electrons, so it overall has 2 hydrogen atoms, and it's going to give these hydrogen atoms to ubiquinone here. And by the way, there are other names for ubiquinone that I should have told you about a minute ago. Okay, so ubiquinone is also called coenzyme Q. Okay, and for short, people often just denote it as Q. And importantly, you'll see that it has this long hydrophobic portion here, which is this isoprenoid polymer. This will embed within the hydrophobic core of the lipid bilayer here. So you have ubiquinone molecules within the lipid bilayer. Okay, so complex 1 has access to ubiquinone molecules. So what it can do is it can now grab a ubiquinone molecule out of the lipid bilayer, and it can give it these 2 hydrogen atoms. Now what happens when you give 2 hydrogen atoms to ubiquinone? Well, basically it's going to turn into another molecule that is called ubiquinol. Okay, so let me now discuss what the structure of ubiquinol is. So, if you want to understand this reaction, what we can think of happening is think of breaking the second of the two bonds between each of these carbon and oxygen atoms in these two carbonyl groups. So think of breaking the second of the two bonds, not both bonds, the second. Okay, and imagine giving one electron back to the carbon and one back to the oxygen in both cases. So now this carbon has a free electron, this carbon has a free electron, and both oxygens have a free electron. This is now going to become a normal benzene ring, because basically, remember really what benzene rings are they are this ring of 6 carbon atoms where each of the carbon atoms donates an electron into a delocalized ring of electrons. I mean, we often draw it as alternating double and single bonds, and that was a theory for many years of what the benzene ring was, and it's a very helpful theory. But we know better now that actually what's happening is that the electrons are going into these orbitals that lie above and below the plane of the ring, and these are called the delocalized rings. Now currently, only 4 of the carbons have donated electrons in. This carbon, this carbon, this carbon, and this carbon have donated those electrons in. And those electrons are being denoted by these double bonds. So basically, this carbon and this carbon have donated electrons in, and that's being denoted as this double bond here. So that's that bond there. And this carbon have donated electrons in, and that's this double bond here. Now what's going to happen is all 6 of them have donated electrons in, but because this carbon and this carbon have now got free electrons, so they're going to donate it in. So you're going to have the complete delocalized ring. So this is going to return to benzene, basically. What if you don't like thinking of benzene in terms of delocalized rings, what you can just imagine doing is breaking this double bond here, breaking this double bond here, okay? Not both bonds, sorry. Breaking the second of the 2 bonds within the double bond. Okay, so giving 1 electron back to each of these carbons. And then you can imagine forming a double bond between this carbon and this carbon, because both of them now have free electrons, between this carbon and this carbon, because both of them have free electrons, and, oh well, you can imagine forming a bond between those 2. So there was no point in breaking that one, but never mind. The point is clear. This is going to become a benzene ring. Okay? So let me draw it out as a benzene ring. Like so. So I'll put alternating double and single bonds, although we know, of course, it's a delocalized ring. Okay? And then off this carbon you'll have this oxygen with a methyl group. Off this one you'll have an oxygen and a methyl group. Off this one, you'll now have a single bond to an oxygen. Off this one, you'll have a single bond to an oxygen. Now, these 2 oxygens both have free electrons still from the breaking of these bonds here. Okay? We are now going to bind the hydrogen atoms that we have received from the NAD onto these oxygens to create 2 alcohol groups. Okay? And now you still have this isoprenoid polymer here, like so. So there are 10 of these. So this then is the structure of ubiquinol. So when these carbonyl groups have been replaced by alcohol groups, and the 1,4-benzoquinone has basically been replaced by just a benzene ring with 2 alcohol groups coming off the 1st and 4th carbons, then that is called ubiquinol. Okay, so basically what complex 1 does is it takes in a molecule of reduced NAD along with a proton from the matrix. It takes the proton as well as the hydride anion from the NAD molecule, and it then has 2 hydrogen atoms, and it binds them onto a ubiquinone molecule, which is denoted now, so it is denoted this time by Q here. And basically, ubiquinol is then denoted as QH2 because you've got ubiquinone with 2 hydrogen atoms, so it's QH2 basically, so it converts Q to QH2. So ubiquinol is usually denoted as QH2. Okay, so complex 1 therefore reduces ubiquinone, so we can now see the logic in the naming of it as NADH ubiquinone oxidoreductase, because it's oxidizing reduced NAD and reducing ubiquinone, because ubiquinone receives the electrons that the NAD molecule was carrying. Okay, so that's the role of complex 1. In the next video, what we'll do is discuss complex 2.